Okay, so hello everyone. Welcome to day 10 of this RH online course. As always, thanks for joining us today. We are going to focus on this class on computing the optical depth at 500 nanometers using RH and for the enhanced network simulation run that we have been using in previous classes. The idea is that we are going to start from the atmosphere that we transformed in day 8, and we will learn how to perform the computation in a very, very simple way. Okay, so then we are basically going to follow the script, the ideal script that we use in day 9, but we are going to simplify RH configuration. So then this will speed up a lot the process, because in this case we are mainly interested on the optical depth vector. And the idea is that with this optical depth information, we can use the Bifrost atmosphere plus this optical depth vector to create an atmosphere that can be used for as input for SER and desire. And I will get into details later, but the idea is that sometimes we want to analyze, in some cases, the behavior of the code, but in other cases, you have a given feature in your simulation, and you want to do some observations with a given spectral configuration, a given set of lines, or with a given spectral resolution, cadence, something like that. And you want to know if with these lines, this configuration, and also using, for example, inversion code, you can extract the information of that specific physical event or feature that you have in the simulation. So then in those cases, as I again will explain later, but in those cases, I think the best thing is to run the synthesis with an atmosphere that is already in optical depth, because the inversion is going to be also done in optical depth. So you are going to compare your output with the input after some transformation. So then the best thing is to have everything in the same format. So for this reason, I think it's very good to have a way of computing the optical depth and have it with a high accuracy that is the one that RH provides. Okay, but before that, I want to have a new section today. It's going to be very briefly. But the idea is that I'm receiving some feedback sometimes, and I think some of the questions are good if we cover them here. So it's going to be very, very quickly, I hope. But every week or every class, I will try to have some information in this slide. So then the idea is that the first thing is that we have a question from Harsh that he has been trying to run, I think he said day 6 class, but instead of using the feel-free instruction in the keyword.input for the Stokes computation, he said full non-LTE, and it seems that it's not converging well. So I don't know if some of you have tried.
I have used FALC. I did not use Bifrost. I was just trying basic. Okay,
so directly with FALC.
Okay. I did with FALC first.
Okay. So then the idea is that I couldn't run the test, but I will do it. So in case you are trying to do the same, you may have the issues and the same issue. So just let us try it, Han and me. And then if we see what could be the issue, I will report it in the next class.
Which atom are you solving in non-LTE?
Calcium. Calcium to BKLM, Barclay calcium atom.
Yeah.
Which is given with a stick.
Yeah. We will check it, because in my case, I have done it with a calcium atom and it worked, but I will just repeat it with this example, but just setting full non-LTE and check what happens. Okay.
Typically, it shouldn't be necessary to solve the non-LTE with full Stokes. I think that's what you meant here.
Yes. So it should say full Stokes. Sorry.
No. The biggest difference is that it uses a different formal solver in this case, and I am surprised it wouldn't converge. But,
yeah. Yeah, I think it requires more time, but the tests that I have done in the past, it always converge. But let me try it, and then
It could be
that's
that you shouldn't put any NG acceleration. But
yeah, I will try. But at least we took note, and then if other person in the online course is doing the same, so just wait a bit. And my recommendation still is that feel free should be the default option, but we will try to check what is happening with full stocks. Okay, and also we have comments from Angel. He's running the programs from day 9 in the IIC servers, and I think he's doing it in parallel, and it seems that it works flawlessly, so it's very good to know that. But he also has some comments regarding the Python wraps, because he's doing IDL and Python class, that is very good. And he said that the Python script for writing the atmosphere converts the input gravity from meters per second to centimeters when doing the writing. But if I remember correct, that conversion is not done in IDL. So just be aware of that difference. And at the same time, the IDL script for writing the atmosphere, it uses kilometers as input and then writes meters per second, I think. But the conversion is not done in the Python. Angel, is this correct? I think you are here, right?
Yes, I'm here.
Hi.
You can hear me?
Yes.
Yeah, I mean, I did it 2 weeks ago, just right after you finished the class, so I don't remember the details now. But I think, yeah, I mean, the idea was that the IDL scripts and the Python scripts are different in gravity and in velocities. One does the conversion and the other one doesn't, so you just have to be careful.
Yes. Okay.
Because I follow exactly the IDL script, and then when I did it in Python, I saw that it was not, it didn't make sense, so I had to do the conversion myself.
Okay.
yeah, there may be some differences.
Yeah.
And one thing is that in the Python case, I made sure that when you read and write, you don't change anything. So it doesn't. It's a bit more careful with the conversions.
Okay. Good. Okay, so then it's just that thanks to Angel for checking this, and also please the people that are using Python programs, just try to follow what I show, but be careful, because if there's some difference, just revise it.
Mm-hmm. Yeah, but the Python scripts worked fine for you for the rest?
Yeah. I mean, actually, I'm not an IDL programmer, so that's why I do it in Python, because I cannot follow the IDL routines properly. So, but the Python one are quite good so far. I mean, I can replicate everything that Carlos was doing with the IDL.
Okay, wonderful. Okay, thanks.
Okay, good. Okay, so then just that. First, that is good to know that Python is working, and just that. So just keep an eye that sometimes there may be some differences. So just be sure that the output of every step that we have in the IDL script is also the same when using Python. Okay, so then I think that's all for today regarding this. So then let's start with the class. So then the first thing is that, as always, we are going to be in RH F1D, and in this case, it will be a folder called Bifrost Synth 500 nanometers. And here we will run 2 IDL scripts. The first one will be Synth Pro, and then we will use this desired format, Pro. Okay, so then let's start with the first one. This case, I will go a bit faster than usual, because it's basically repeating the previous program, but I will stop a bit on the things that have changed a bit. Okay, so then we are basically going to read the atmosphere from day 8, and we are going to run the same program, but in this case, we simplify the RH configuration. So then this means that we are going to set all atoms to passive. We are going to we are not going to provide any Kurux.input information, and also there's no wave file in the keyword.input, so it's commented in this case. So then this is the simplest way of running RH. Okay. And again, even in this case, as the optical depth at 500 nanometers is computed from the background opacities that are computed from the passive atoms in this file. So then it will be the same optical depth that you can get when running an LTE atom. Okay, so then for just having the optical depth at 500 nanometers is the best approach. Okay, so we define the horizontal domain as the previous class. We are going to select a smaller field of view than the total simulation domain. I plot the same plot as previous week, so it's this one. So we are going to focus on this region highlighted with dark lines, and we have strong magnetic field in these regions. And then we have some areas that are they have a weaker magnetic field. Okay, so then we define the dimensions of the arrays that we are going to store, that they are just basically the domain that we have just defined previous lines. And then we will have a vertical domain that is the one that from the shortened atmosphere that we had in day 8. If you remember, I think it was from -500 kilometers to 3,000 or something like that. So this is the same one. We are going to use it here. So then the first thing is that we are loading temperature, line of sight velocity, electron density, hydrogen populations, and the 3 components of the magnetic field from the previous class. If you remember, these are in RH units. They are reversed. So the first height index is the top of the atmosphere. And we are just selecting the horizontal domain that we saw before. Then we need to define where we are going to store the optical depth values. So this is the array we are going to define, and it has the same horizontal dimensions, or this dmax and dimension y. And it also has height extension, because each geometrical height has associated an optical depth. Okay, so it's a three-dimensional vector array. Then we are solving the radiative transfer equation, and in this case, even if everything is set to passive and no Gudiksen file is provided, not web file is provided, the code is always computing the intensity at 500 nanometers. So we are going to save that value as well, because as we said in the previous class, it's good to have it, because if this array looks fine, then we can assume that at least some of the computation was done properly. But if we have some issues, if some pixels look wrong or something looks off, then we have a problem with our configuration. Okay, so then in this case, we run as the previous class, the synthesis. And if you remember, we run a loop that covers all the horizontal domain, so each X and Y pixel. And in each run of the loop, we load the atmosphere for that specific pixel. We write it on this kind of file for RH. So in the thermal part as a .atmos, and then the magnetic field as a .b file. Okay, so it's basically the same we did last week. We don't have microturbulence, so we just write the name and then provide atmosphere and write atmosphere. The same with the magnetic field. And then we run RH. We also run solve rate, because we are just repeating at last last class program. So we are solving the intensity, the continued intensity at heliocentric angle equal 1, mu equal 1. And we read everything. And if you remember, the information related to the optical depth was included in this ideal structure. So this geometry.tau. And also it was in natural scale. So we are going to use it in log scale. So we already take the logarithm and we are saving the logarithm of the optical depth at 500 nanometers. As before, we are going to save also the continuing intensity at 500 nanometers. And in this case, it's simple, because the Stokes I, the array.I array only contains 1 point. So it's just 0. Okay. And then if you remember, we put a print just to know more or less of which part of the loop we were running. And then I was closing this just to be sure that no unit was open after running multiple runs. And in this case, you can try it by yourself. It's going to be much faster. I think around 30, 45 minutes, depending on your computer. It will be done the same field of view as a previous class, because now it's really, really fast. It's just running LTE. Okay. And then, as before, we also save the wave file just to have it as a reference. And then we are going to save all the information we use in this run. So the initial X point, the final Y point, sorry, the initial Y point, the final X point, and the final Y point, just to know if in the future you want to check which part of the snapshot you use, just to have it here. It's usually advisable. And also we save the dimensions. This one we use later also. And we save the wavelength and the optical depth array, the continuum intensity, and also just as a reference, I recommend you also to keep the geometrical height also, because later on it could be good to be sure which vertical domain you use in this computation. Okay, so then the summary for this first part is just we repeat the same example from last class. We simplify the RH configuration. We tune a bit some things, but essentially it's the same run. And what we are interested here is on the optical depth information. And as we are simplifying a lot RH, it's going to be really fast. Okay. So then I think I went too fast, but it's basically what we did last week. So just in case I went too fast or really fast, is there any question before I move to the new elements of this class? Okay, so then just let me close this one, and then we move to this part. Okay, so then the idea in this case is to use the optical depth from the previous one, okay? And we are going to prepare a cube of data that will be ready to be used in design and serve, okay? And I think most of the inversion codes will be able to use it. So sorry for the interruption. And then the idea is, as I said before, and I will say it a bit slowly here, when you run the inversion, at least with set and decide, and I think in general, most of the codes that you have there, you will work on optical depth scale. So then your results will be temperature, magnetic field, velocity, but all of them will be in optical depth scale. So you could try to run the synthesis using geometrical height and then embed those profiles with a given inversion code. So at the end, you will have the output atmosphere in optical depth scale, and you would like to compare that with the initial atmosphere to check the accuracy of your results, or to check if your lines and your configurations are sensitive to what is happening in the atmosphere. So then it's not straightforward to compare optical depth and geometrical height dependent atmospheres. So then what we did, for example, for the design paper was to transform the Bifrost atmosphere to optical depth as precise as possible, then use that as an input for the design code. So then we generated a stock spectrum, and then you can add noise, you can add instrumental effects, and then you do the inversion. But the idea is that the output atmosphere will be in optical depth scale, and your input was also in optical depth scale. So if you want to compare the results, it's just straightforward. So then what we are going to do today, as the best way we have for computing the optical depth is RH. So we are going to do inside the RH online course how to transform or how to create the Bifrost, transform the Bifrost atmosphere to desired format. Okay, so then we use the Bifrost atmosphere for that, plus the optical depth information that we got from the previous run in RH. Okay, so then we load the results. Here you have the information because we are going to use it later. And we start, as we said before, plotting the continuum just to be sure that the results are reasonable. Okay, so then here we have that as the previous class, it looks fine. We have granulation, we have intergranules dark, or the lower intensity. Granules, they have a larger intensity. And then we have the regions with strong magnetic field. They also have brighter intensity. That is what we usually see when observation. Okay. So then we can say that in principle the run was correct. So then let's move a step forward and then let's try to get a feeling of the optical depth. Okay. So then the idea is we can plot the optical depth, the spatial distribution of the optical depth at a fixed height. And just the warning is that our array is like this. So you can pick a given index that corresponds to a fixed geometrical height, but the optical depth will vary. Okay, so it means that this is what we revised in previous classes. So for a fixed optical geometrical height, the optical depth will change depending on the configuration of the atmosphere, the magnetic field, and other things. Okay, so then let's try to look what I'm trying to say, and then you will see what I mean. So let's pick 3 reference heights. So we have the vertical domain, the geometrical height from the previous run. We save it in the IBL save file. So I picked these 3. So the geometrical height 0, 500, and 1,500 kilometers, because we can say that this is essentially the bottom of the photosphere, middle upper photosphere, and then 1,500 kilometers is chromosphere or lower chromosphere. Okay, so then we are going to plot the optical depth, the spatial distribution of the optical depth at those 3 geometrical heights. Okay, so then I'm just using this array for the full domain and then at these 3 index. Okay, so then let's check how this looks. And it's this one. Okay, so then let's make it a bit bigger and then let's go one by one. So the optical depth at geometrical height 0, it looks essentially like the granulation. So this is nice. But you see that we have that granules, they have a given optical depth, then intergranules, they have a different value, and then also the strong concentration of magnetic field, they produce a specific value of the optical depth, in general, lower values of the optical depth. If we go to 500 kilometers, the spatial distribution looks a bit more complex to understand, but still we see that there's a trace of specific optical depth values for those regions where the magnetic field is stronger. So you see that what was darker in this side, the left side, is still darker or lower values than the other areas. Okay, and then if we go to 1,500 kilometers, then here is it's even more difficult to understand why the optical depth is doing this. But for me, the interesting thing is that you see that now there are a lot of thread-like structures. So then we have there what we assume, or we usually say that is the chromospheric pattern, where things are elongated, and sometimes things are started on magnetic field concentrations, they are elongated and then expand away much farther than in the photosphere. Okay, but the important thing is it looks smooth and it doesn't look crazy. So then we can assume that in principle the computation of the optical depth is reasonable. Okay, so then with that we can continue. And then what we're going to do is, now the final step is how we complement or how we combine that optical information with the Bifrost atmosphere to create the design-ready Bifrost atmosphere. So essentially, I think you have mainly two options. So the first one is that we already transform the atmosphere for running RH, and we have it ready, and it's the same domain that we have the optical there. So we could use that and then adapt it to SER and design. Or the second option is to just read the raw Bifrost, the original Bifrost atmosphere, and then transform it to SER. I choose to do the second option because I think it could be easier, but we can also do option one. The idea is that option one would mean reversing some of the changes that we did. So if you remember, we changed units sometimes. We also changed the index, so top to bottom and the opposite. And I think that was mainly all. So I think that could introduce more errors than just taking the raw atmosphere, the original one that we know exactly how is configured in terms of units and growing axis and things like that, and just adapt this to SER. Okay, so then let me show you what I mean, and if you have any question, just stop me on the go. Okay, so then what I did is just to make it as self-consistent as possible. I downloaded again, or I moved the Bifrost snapshots to a folder inside this folder. So if we go to here, so where I'm running the script, there's a folder, and here you have the Bifrost atmosphere. So you don't need to go to day 8 or something like that. So everything is here. Okay. And then we're going to read the different atmospheric parameters and change them to SER and design format if needed. Okay, so then we start with the temperature. If you remember, it was the log of the temperature, so that we just need to do this transformation to have it in a natural scale. Then we have the geometrical height. If you remember, it was an extension. It was it's included in every atmospheric parameter, but as an extension. So in ideal, you can read it this way. And we move it to kilometers because we transform it to kilometers because it's how we need it, how we use it in SER. Then we load the line of sight velocity. In this case, there are two transformations that we are going to do. The first one is that it's in meters per second in SI units in the Bifrost run, but we need centimeters because SER and design work in CES. So we need to multiply by 100, but also we change the sign of the velocity. Because if you remember, they were using what we can call the theoretical sign, and design use the spectroscopic, I think is the convention, spectroscopic sign. Okay, we continue with the magnetic field. Again, this also is given in SI units, so it's Tesla. So we change it to Gauss, just multiplying by 1 10 to the minus 10 to the 4. Okay, and then electron density, we read it from Bifrost. It's in log scale, so we put it in natural scale, and also we change it to CGS. And this case is divided by 1 to the 10, 10 to the 10. Okay. Now, in the case of SER, the codes also uses gas density and gas pressure. You remember the atmosphere had 11 columns, and the 3 last columns, they were geometrical height, gas pressure, and gas density. So we are going to read it now. It was not used in RH, but we add it here. And it's as before. So it's in log scale. So we put it in natural, and then we change it to CGS. I hope the change, the transformation are correct, but if you run in the programs, you find that I made a mistake, just let me know and I will revise it. And then here the same, so we read the gas pressure, we put it in natural scale, and then we transform it to CES, okay? So now we have the Bifrost atmosphere, the full map in the correct units and convention for SER. Okay, if you remember, SER needs that the first index is the bottom of the atmosphere, and the original Bifrost atmosphere, the first index is also the bottom. We need to change it for RH, but in the case of SER and design, we can keep it as it comes from Bifrost. Okay, but in day 6, when preparing the atmosphere, we cut the vertical domain because we said that it was too large. And now we need to cut it again. And we need to be careful because it has to match the same vertical domain that we use in RH for computing the optical depth. So remember that we have an optical depth that is vertical, so it's a 3-dimensional cube. So the height domain should be the same one that we are now going to use for defining temperature, velocity, and magnetic field. Okay, so this is the same sentence from day 8. And now we are just cutting. Okay, so Harsh, do you have a question?
Yes, hi. So you said that you will be using same lower and upper indices in the atmosphere to cut to provide those SER or desire. So my point is, generally when you give input to inversion codes, you generally try to keep it between like -8 to 1 log tau. But as you have already mentioned that log tau is actually will be different at like different heights for this different pixels. So ideally you should have this lower and upper indice different for different pixels rather than same for everything.
Yes and no. So if you wait a few minutes, I will show you that later we interpolate. We can interpolate the atmosphere to a uniform optical depth. So then in that case, the input will have a regular and uniformly spaced optical depth. And you can use, in fact, the same type of atmosphere for the inversions. So then the input and the output will have the same optical depth range and step.
Okay.
Okay.
All
okay.
right.
Okay. But
Thanks.
thanks for the question. Okay. So then I will show you later. And in case that later you don't understand what I did, just ask a question. Okay. Thank you. So then what I was saying is that now let's cut the vertical domain to match the same vertical domain that we use with RH computation. And also, as we are loading the original Bifrost atmosphere, so this is the full cube. So we have this initial X, final X, initial Y, and final Y from the previous run that we save it in the ideal save file. So we just use it and we keep, so we maintain the same also horizontal domain. Okay. So then the next step is the magnetic field. So if you remember, for RH, but also for SER and design, we need to have it in spherical coordinates. So then it means that the Cartesian format that we have from Bifrost needs to be translated to a spherical, and we did it in last week. So it's just running this loop, and then we have it in spherical. Remember that before I changed it from Tesla to Gauss, so we don't need to add an extra translation for the field strength, but the output, at least in IDL, it's in radians, so then we need to transform it to degrees. Okay, so in this case, we use the ideal sentence that is degree to radians, and then we just use it. But probably in Python, there's a similar way of transforming it. Okay, so then the next new thing that is different from the previous 2 classes is that we have electron density from Bifrost and is directly used in RH. But SER works with electron pressure. So then what we are going to do is transform the electron density to electron pressure. And this is done using temperature and the Boltzmann constant. So I define it here. And then the electron pressure is the electron density, the array, times this constant, times the temperature. Okay. I think this sentence is valid in IDL. I was checking it and I think it works, but I don't know if you can do this directly in Python, because this is a 3D cube. This is also a 3D cube. So I don't know if this can cause you a problem. So just be sure that the output is similar to what I have in the at the end in the save file. Okay. So then at this point, let me just stop and take a second to just revise what we have done. So we have from one side loaded the result from large H computations or computation, where we have the optical depth array and also the information of the spatial domain and the vertical domain. Then we have loaded all the original Bifrost atmospheric parameters required for set and decide. We have transformed them to SR, so decide units, and we cut it to match the horizontal and vertical domain that we have for the optical depth array. Okay, so now we just need to mix this and in fact check that everything is working. Okay, so then just let me run. So we are design format. I think we had some, this was the first figure. This was the, I forgot to run this, but just let's quickly check. But because I put some stops and prints. So then in this case, was just printing the geometrical height corresponding to this index. So you can see that is here. Then the next print is after the figure, if I'm correct. Yes, 112. Then the next thing is, this is just loading the Bifrost atmosphere. And then now it's transforming the magnetic field in this loop. Let me see here, this loop. And then it stopped here, okay? So then here is just a double check to be sure that the original, the optical depth that we got from RH has the same dimensions than the one, than the temperature, for example, that we have just reformatted from the original Bifrost. So then you can see that the spatial domain is the same and the vertical domain is the same, okay? So then one thing before just mixing everything is that if you remember, we change the index, the first index corresponds to the top of the atmosphere in RH. This means that also the optical depth that we got from RH corresponds, the first index in each pixel corresponds to the top of the atmosphere. And RH and the side needs the opposite one. So then we need to reverse the optical depth array. I do it in a loop. So in each, I go for the full 2D domain. And in each case, the only thing I do is just reversing the top to the bottom, okay? And then in this case, I wanted to double check if the original one at a given index has the same value as the new one at the reverse index. So then what I'm saying is, please print the maximum of the difference between all the spatial domain in optical depth at a given index, in this case 46, for example, minus the new optical depth that has been reversed over the full domain and the reverse axis. So the maximum was 173 minus this one, and then we need to add one because how ideal works. So then if we just put this, then the difference is 0. So then it's an additional double check that I'm always wanted to do. And this means that it's really the reverse axis array. So with this, we can feel a bit more confident that what it has done is correct. Okay, so then this is the part that I think is related with Harsh's question. So the idea is, at this point, in principle, you can use the array of combining the Bifrost atmosphere plus the optical depth to run synthesis in design. But I prefer to interpolate the atmosphere to a uniform optical depth for various reasons. The first one is that when you plot, for example, the temperature and your optical depth, so it's not related to a uniform optical depth, you can see things that are not what you are used to see when you see observations, for example. And in fact, I think someone mentioned that a few classes ago when we were plotting the temperature at geometrical height equals 0. And the second one is essentially for simplifying the comparison. So if your inversion is going to be done in a uniform optical depth scale that, for example, in this case, goes from 1.5 to -8, then the best thing we can do is also to have the input atmosphere in the same scale. So then it will be just easy to compare, for example, the results at log tau -1, log tau 0, log tau -5. So then I think that there are two main reasons of visualization purposes. And I think it's easy to handle them when you make a 2D plot, and also for simplifying the comparison when you're doing inversions and comparing with the input. So then in that sense, I'm going to create a uniform optical depth vector that has a log tau step of 0.1. It has 96 points just to cover this range with this sample. Okay, and then I just create it. So it starts in 1.5 and then it's decreasing towards the upper value. So it means it starts in positive log tau values and it ends in negative log tau values that correspond to higher layers. So if I just put here this, you can see that the first value is 1.5 and then the last value is -8. Okay, so then what we are going to do now is to interpolate the new atmosphere, the Bifrost atmosphere, to this, and the optical depth information to this uniform optical depth. Okay, so then we are going to do it in a loop, and also we are going to use the opportunity to save the results in an array that is with the same format that we will use for running in parallel design or SER. So then the array should have X and Y dimension, the horizontal domain, then a vertical domain, and then 11 columns. And if you remember, the 11 columns were optical depth, temperature, electron pressure, microturbulence, field strength, velocity, inclination, azimuth, and the three last components: geometrical height, gas pressure, and gas density. Okay. And just as a warning, before I forget, please, it's not end set. Remember that before the domain was defined by the geometrical height. So now our cube, it's defined by n tau, and this n tau is defined here. Okay, so we are going to interpolate a new grid, and this one is the one that's going to give us the vertical domain. Okay, so then we run a loop for each pixel. And what we do is that the first item is optical depth, so we don't need to change it. In fact, we could define this outside the loop, but I just wanted to have consistency. And then we interpolate, and what we are going to interpolate is the temperature at a given spatial pixel, defined by I and J, the full vertical domain. And then this is the reverse optical depth array from RH. So then we will have that is spatial dependent. So each I and J pixel has a different optical depth vector. And then we interpolate that with our uniform optical depth vector that we defined a few lines before. Okay, so just let me revise it again. It's the temperature of each pixel that is given by Bifrost, the optical depth vector for each pixel that we obtain from RH, and then interpolate it with a uniform optical depth that we have just defined. Okay, and we do this for all the atmospheric parameters. Here you have that we do it for pressure. This is microturbulence, so we don't have information, so you can add values here. I just put it that if you add them, should be in centimeters per second. And then we do the same for field strength, line of sight velocity, inclination, azimuth, and then the other three quantities. I separate them because in principle, if you remember, they are not the main quantities that we use in the inversion. So they are computed after solving the full cycle and inversion. So I just put them a bit different. And in principle, I think if they are 0 in the synthesis, it should not be a big problem. But as we have them, it's good to include them there. So I just put it there. And one last thing is that I put out here and Basilio, because maybe Basilio cannot. So you see that for temperature and velocity, I'm just interpolating the same atmospheric parameter that we have. But for pressure, for example, I'm taking the logarithm of pressure, I'm doing the interpolation in log scale, and then I'm putting back in natural scale using this exponential instruction. So I think Basilio recommended that because as they are very, very small quantities and they change a lot with height, it's probably better to do the interpolation in log scale.
Yeah,
This,
in fact, the gas pressure and electronic pressure behaves more or less linearly in the logarithm. It's like an exponential. Then
okay.
It is a better approximation. Yeah.
Okay. Okay. Thank you. So then it's just that. So if you see that there is a bit different some instruction respect to the other, it's just that. So pressure, so I mean electron pressure, gas pressure, and density, they are done in this way. And the rest of the physical atmospheric parameters are done in the natural scale. So this is node 1. Node 2, as I said, we don't have information of the microturbulence, so we leave it like it is. And then node 3. So now be aware that I'm also interpolating the geometrical height. And if you remember, it was constant and it was the same for each pixel. But now we are going to interpolate it based on the optical depth information. So now we are going to do the opposite. So our array will have a uniform optical depth vector. And for each spatial pixel, we will have a different geometrical height domain that is governed by that optical depth vector. So I will show you a plot later. But the idea is that now we are in the opposite situation. So before we had uniform spectral, height step in geometrical height, and the optical depth was different. And now we have the opposite. So now our optical depth is uniform, but our geometrical height, when we cut a given optical depth, it will vary. Okay, let's check that. I think this is everything. And then just we write the result in a fits file. So then this is already ready for running in parallel design. Okay. So before doing anything, just let's make a context plot. So then what I'm going to plot is in this one, in the index 1, is the array test, and its first 3 index, so 15, 35, and 55, that corresponds to log tau 0, -2, and -5. This is in the uniform optical depth vector. And index 1 is temperature. Okay, so we will have the temperature at 3 optical depth. Then we're going to do in the same plot, we're going to do the same with line of sight velocity. So the middle row will be velocity at 3 different optical depth. And then in the bottom part, just to show you what I meant about the geometrical height, we will have the spatial distribution of the geometrical height for a fixed optical depth value. Okay, then let's go here, and then let's load this one, and let's check how it looks. Okay, so then I will make it bigger, and then we will go row by row. That's not too much. So then in the case of temperature, now we have that the temperature at optical depth 0, it looks, I would say, natural for those that work with observation, in the sense that granules are hotter, intergranules are cooler, and then you have bright regions in the locations of strong magnetic field. Okay, then if you go a bit higher, then you have the observed and so-called reverse granulation pattern. So then in this case, granules are darker and intergranular lanes are brighter or hotter. And then you have something, let's say, chromospheric pattern, because it's complex, and as we said before, it has intricate patterns. So, and we can say that it's dynamic, but this is what we have. Okay. And then if we go to the velocity, it's the same. So first we check that the sign is correct. So a positive velocity, that mean down flows for SER and desired, and they are located in intergranular lanes. And negative velocities mean upflows for desired, and they are located in the granular areas and surrounding areas. Okay. And then if we go a bit higher, we see basically the temperature pattern. So it's also a reverse granulation, and the velocities are also a bit different, but in general, they tend to decrease with height, at least around this region. And then we see, again, a similar pattern as above, where we have strong velocities and complex changes of sign. Okay. And then let's go to the geometrical height. So now we have an array, and we have fixed an index in optical depth, and you can see that there's a special distribution of geometrical height. And in fact, it's compatible with what we know. So what I mean is that we have that photons at a given optical depth, they come from deeper layers when the magnetic field is stronger. So you see for this reason that it's minus 150 kilometers before zero. And then photons from granules, they come from higher layers. And for example, in this case, around 100 or 150 kilometers. Okay, so we have reversed the concept that we had before. So now we fix the optical depth and we check from where photons could come, just checking this special distribution of geometrical height. Okay, then things become a bit, let's say, complicated as we move up. And then in the case of log tau -5, we have again threads and complex pattern, but at least it looks consistent, mainly here. So here we can see that what we know just by general knowledge of solar physics is that photons, where the magnetic field is stronger, we have the Wilson depression, and they come from deeper layers. Okay, so then so far I think so good. So then let's make a second plot, and this case is so this is what I said, so I think I don't need to. Yeah, just one thing, we were talking about optical depth. In the next class, as I already finished the computation and just checking that everything is consistent. So in the next class, as we will check later in the presentation, we will check the height where optical depth is unity, but for the spectral range of calcium, 8542. So we will add information on what we are seeing today. So I hope it will be helpful. But let's go to the next plot. So in this case, we are going to make, again, 3 rows with 3 columns. Columns will be different optical depth, and the rows will be the 3 components of the magnetic field. Okay, so then it will be index 4, that is field strength, and it will be 3 optical depth values. Then index 6, that is inclination, and then index 7, that is the azimuth. Okay, so then let's go to this one. So again, let me go panel by panel. So in the case of the field strength, we see that this was more or less what we had from the geometrical height atmosphere. But now again, it looks for me natural that you see that as you move a bit higher, it's getting a bit blurred because the magnetic field is getting expanded due to the reduction of the gas pressure. And then here we have a different configuration, but it's again, it looks interesting because we have the magnetic field has this complex and I would say again dynamic shape. So it's nice. I think it's working correctly. And then the same here. So we have that the magnetic field inclination is very, so it's pointing toward us or opposite to us in the regions where we have magnetic field because it's a network patch. And then we have different configurations when we move from there. Then following the expansion of the magnetic field, also the inclination is also a bit different. And then here we have a complex pattern where, yeah, it looks interesting. Okay, so, and then the azimuth. Azimuth for me is always difficult to follow, mainly in the quiet sun. In an active region is better, but I would say that this is what you expect from a quiet sun azimuth. It looks, yeah, it looks like an azimuth. Okay, so then let's see what we have left. Yes, so then basically we are now in the summary. So then let me revise again what we have done so far, and then we can check if you have any questions, and then we will go to the presentation again. So essentially, we use RH for get information of the optical depth. We did it in the simplest way, so it was very fast. And we knew how to prepare the atmosphere because we have learned in day 8. So then having this optical depth, we then loaded the Bifrost atmosphere. We transform it to SER format, and we combine it with this optical depth. But the idea is that we wanted, or I recommend you to have it in a uniform optical depth scale. So we did an interpolation in the process. So then in this case, what you have is that if you use this atmosphere as an input and you run the inversion using, for example, the same optical depth vector or a different one, you just can compare one-to-one the results. And also when you plot at a fixed optical depth value, the temperature, it looks more or less like your observations usually look. Okay, so then just let me confirm that I have everything, and then I will go to Ryan that has a raised question. Just 1 second. Yeah, so then, yes. So then Ryan, do you have a question?
Yeah, thank you very much for this. This is very useful. I have a very stupid question that I'm embarrassed to ask.
No, it's okay.
The optical depth scale that SIR and Desire use, you take the log of the optical depth of 500 nanometers, but is this the natural log or the log to the base 10?
Yeah, it's a good question. It's base 10, right, Basilio? Yes, yes, yes.
Base 10,
base
okay.
10. Yes,
okay.
Yes, I think, yeah, 1 second. Yeah, sorry, I should mention that. So here, this in IDL, it's the log scale 10, okay? So then this is the one that we get from RH. Okay, yes. Okay, so then is there any question, additional one?
No, I was saying with the mute
Yeah.
mode that you are you are calling tau to the log tau. Yeah,
Yes.
this is only for confused people.
Yes.
I use the same strategy.
Yes. 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 Oh, really? Okay, I will check
yes,
it.
you are calling tau equal
Okay.
to the log
Okay.
10
Okay.
of
Okay.
tau.
But did I did it correctly in the? Yeah, I did
yeah,
it
here,
in the plot.
not
Yes.
in the variable. Yeah.
Yes, I'm not probably speaking either. So yeah, yeah, it's just for checking if people are attending and listening, listening the speech. Okay, so then I think I hope this was useful. Here, I think I put it. Yes, I put it some personal comment, and I think it could at the beginning it could seem that is a bit not straightforward, that you need to run RH for computing the optical depth, for creating an atmosphere, for using it in design. But I think even if there are different options, I think the most accurate way of having the optical depth is to run in RH. And as you saw, in general, it's not difficult to prepare the atmosphere, just require having knowledge of the units and things like that. But all this work that you need to do to have everything in the best format for design, it would pay off in the future, because running an inversion that it takes like 2 weeks and then spending a lot of time trying to see how you can compare your results with the input atmosphere, I think it's worse than just dedicating a bit time to do this. And at the same time, I think also for visualization purposes. So if you remember plotting the temperature at Z equals 0, geometrical height equals 0, the spatial distribution was not the one we usually have from observations. While now that we have interpolated everything to optical depth, to a uniform optical depth, and we have that information, the temperature look like the one that we have from a continuous intensity in any observation. So I think it's also good for just being more comfortable and too easy translate from one to the other. But I assume that it could be a bit difficult to follow all the process of RH and then reading and then interpolating. But if you have any questions or you feel that we could do it in another way, just let me know. Okay. So, okay. So then, Alberto, hi, how are you?
Fine, and you?
Good,
So I
good.
have a question. I think what you are suggesting is probably the correct way. I see the point, but let's say that I didn't before.
Okay.
So my question is: have you quantified how much is the difference between making what you did, and now you take the magnetic field at log tau -2, and doing the synthesis from Bifrost numerical model, making the inversions, and then find log tau -2 in the Bifrost model and compare the magnetic field with the. So you have a comparison between the magnetic field recovered from the inversions on Bifrost in height scale, in megameters or whatever, and another with optical depth. And then from the one that you have in height, you calculate log tau and you find where these log tau values are in your numerical model. How much is the difference?
Yeah, so I'm not sure if I've completely follow, but I think the main cause of difference could be of how you compute the optical depth of the input. So are you using, for example, the SER routines for computing this optical depth?
Yes, or even if you have computed here the optical depth,
Yes,
right?
Yes.
But imagine that you have done this after you have done all the inversions or all the synthesis and then the inversions, and then say, okay, now I have my optical depth here. So the difference is, in one case, your synthesis comes from a numerical model in optical depth, while in the other case, the synthesis comes from a geometrical scale. And then the one who, what is it? Yeah, sorry.
Yes, no, so well, Basilio was going to ask to say something, but just 1 second, Basilio. So Alberto, I think the one of the questions that I have is that internally, when you do the inversion, the code is working in optical depth, right?
Yes.
So then the idea is this optical depth is the one that you should use.
Yes.
So then I think
no, I understand. I understand all that you have explained today, and I think is probably the proper way to do it. But imagine that for any reason you did the synthesis from geometrical scale, and you have a synthetic profile.
Yes. Yes, but what I mean is that in the code you provide as an input geometrical height and atmosphere in geometrical height format. But internally, the code computes optical depth at 500 nanometers.
Yes.
So then, if you take that optical depth and you use it as for transforming the original atmosphere, as I did here, it should work. So what I mean is that, are you using that optical depth, or you're computing?
No, unfortunately, I mean, the problem is that sometimes, imagine that you are working in a team, and one part of the team has the numerical simulation, that there are huge data, and they say, okay, we cannot transfer, blah, blah, blah. We are going to synthesize.
Yes.
And then you get the synthetic data.
Yes.
And you have the spectra, and then they did using height scale. So then you say, okay, I have a spectra that calls for a numerical model. That is correct, right? And then you say, okay, now I need the optical depth. I'm going to compute the optical depth from that numerical model because for any reason it was not safe. Okay. So then you made the inversions, and then after the inversions, you compute the optical depth of the numerical model, and you compare at the same optical depth.
Yes.
So
So I understand your question, and I think Basilio may help me. But my question or my concern is that, so for example, if you use the same method for computing the optical depth that was used, for example, in the synthesis, and later it should be fine. But for example, imagine in this case that is an issue that I had in the past. So if you run the synthesis with RH, okay, and you provide geometrical height, and you can also infer the optical depth. So if you take the same atmosphere and you use, remember the modelador program that we had from SER. So the optical depth values from the two programs, from SER and RH, are different. And in fact, in the case of SER, when the temperatures go above 10,000 Kelvin, that is basically the chromosphere, it's wrong. So then the only issue that you could have is that if you use a program for computing the optical depth after the inversion, and it's not the correct one, then you cannot do the match. But if you use, for example, RH, then the optical depth that you get, it should be fine enough. But maybe Basilio wants to
no, perfect. No, I only want to add that you have an additional problem when you are working with synthetic data, from instance, from geometrical height stratification. When you invert, you obtain the result in optical depth. You can get the geometrical height corresponding to this optical depth, but you have lost information of the boundary condition. And then you are using that the zero of height is in tau equal 1. Then because you have lost the information of the Wilson depression, then you cannot go back because you are losing information. I mean,
but I'm not going back to optical to geometrical scale.
Okay.
Okay.
No. In this case, no, there is no problem.
Yes.
In general, the code behaves well enough.
Yes. So my main suggestion is that if you computed the optical depth in the same way that was done, so I mean same background opacities, and even if the same source, then it should be okay just transforming your input atmosphere later after the inversion. But the idea is that it should be the same one. And in our case, for example, I always use modelador from SER to transform in the atmosphere when I was working with SER. But for design, we realized that, well, Basilio knew, but I realized that transforming an atmosphere, the Bifrost atmosphere, going up to 3,000 kilometers with the modelador routines, it will not work. So the optical depth that you get from there and the variables are wrong. So then if you are working in the photosphere, it's fine. But if you work in the chromosphere, the transformation should be done properly. And it means that with SER, you cannot transform the upper layers because the background opacities and the code itself doesn't work above around 10,000 Kelvin.
Okay. Thank you very much. Thank you.
Okay, thank you. I think it was a very nice question. And I think, is there any other question? Okay, so then just let me go back to the presentation, and now we are almost finishing. So then as homework, as always, try to run the example I prepared. Try, if possible, to run the ideal script, and if not, try to replicate it as much as possible with Python. This just as an extra exercise, if you have time. Here, I think it would be interesting to just take in the ideal script or from the save file from day 8, the atmospheric parameters in geometrical height and compare them with those that are interpolating to a uniform optical depth. So you can see the difference between being in a uniform geometrical height scale and being in a uniform optical depth scale. Okay. So then next class, following, I think, Dato's question, that how we compute the height where the optical depth is unity for a given wavelength. For example, the calcium 2 8542 line core. So then I prepare the programs. It will be very easy because it's essentially the same programs as before. So we will check it how to do it next week. And the good thing is that we will also check how to move from there and do additional studies like for example, this one, sorry for the self-advertisement, but these type of figures that you usually see in the literature, and you said, how can I compute that? So we will learn how to do it. So what we are plotting here is, this is a cut of the Bifrost simulation, a horizontal cut online, and we have vertical domain and horizontal domain in this direction. And the idea is that the dashed line, the black one, is the height where the optical depth at 500 nanometers is unity. Okay, so it's lockout 0. So it's the one that we saw. So in the magnetic field patch, it goes down, and then in the granules, it goes up. And then I added the information where the tau is equal unity, the log tau, well, no, tau, in this case is tau, tau equal 1 for different lines. In this case is potassium D1, I think, in green, magnesium B2 and B1, I think B1 is blue and B2 is orange, and then calcium 8542. Okay, so next week we will be able to plot this pink line over this example, and then you will see how to do this. So then you can understand, I think, better this type of plots that always are difficult to know how to really make them. Sorry, and the yellow, dash yellow is beta equal 1. Okay, so it's the height where plasma beta is equal 1. So then it drops for the magnetic field, and then it just changes abruptly in other case. Okay, so I hope this is interesting for you. So we will do it in the next class. And I think after that, probably we will get to computing numerical response functions. And then after that, probably we will move to parallel computing, so arranging in parallel. Okay, so then next class in 2 weeks, Friday 29th. And before wishing you a very nice weekend and a week, do you have any last question? Okay, so then I assume that it's a no. So then thanks again, everyone. It was nice to see you and to hear your questions. So I hope to see you in 2 weeks. Okay.
Thanks to you, Carlos.
Bye.
Thank you.
Bye.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
Thank you, everybody.
Bye.
Bye.